Okay, so now we'll take a look at how we can determine, first of all, when a matrix is invertible, but also if it is invertible, well, what's its inverse, right? Those are the two questions that are at hand. We'll start with the case of 2 by 2 matrices because that's by far the easiest case to answer. In fact, we can answer it completely just in terms of a formula that involves the entries of the matrix. So if we have a 2 by 2 matrix A and I've written the entries as A, B, C, D, starting with the first row and moving on to the second, it turns out that that matrix is going to be invertible exactly when, if I consider the product of the entries on the main diagonal and multiply the two entries A and D, and then I subtract the product of the other two entries, B and C, it turns out that A is going to be invertible exactly when this quantity is not 0. And in that case, not only can we say that, but we can also say what the inverse will be if that quantity isn't equal to 0. So in this case, we can say that A inverse is going to be equal to 1 over, well, what actually exactly the expression we just discussed. So 1 over this quantity, AD minus BC. But that's not a matrix, that's just a number. That's a scalar that you're going to multiply onto this matrix. And what you're going to do is just, you can obtain it from these four entries, just swap the D and the A so that they trade places. And then for both of the B and the C, just introduce a negative sign. So replace the B with a negative B and the C with a negative C. So that's your formula for a 2 by 2 matrix, or pardon me, for the inverse of a 2 by 2 matrix. And notice that this AD minus BC, that's on the denominator of a fraction. So this won't work if that's equal to 0. And that's consistent with the fact that we said that, well, the matrix A doesn't have an inverse if AD minus BC happens to be equal to 0. It only works if that quantity is not 0. And then in that case, it's okay to divide by that quantity because you can divide by anything as long as it's not 0. Okay, and this quantity here is important enough that we actually give it a name. For now, I'm just going to mention it, but we'll study this in more detail later. But it's worth mentioning now. We call this quantity here the determinant of the matrix A. So for now, let's just write the following. We write that det of A. Actually, let's do it this way. Let's say the det of this general 2 by 2 matrix is equal to A times D minus B times C. So this det, that's short for determinant, and we'll study those in much more detail later. But for now, I'll just mention this as a passing remark. Okay, so really, you could say a 2 by 2 matrix is invertible as long as its determinant is non-zero. And if that's the case, if its determinant is non-zero, well, here's the inverse. Okay, let's do a quick example. So we've got a 2 by 2 matrix A given here. 1, 2, 3, 4 are the entries. So find its inverse if it exists. Well, the first thing we're going to do to check if it exists is we'll take the determinant of A. So the determinant of A, this is another way to write determinant. If you want to just reference the name of the matrix, just plug that into the determinant function. So the determinant of A is going to be 1 times 4 minus 2 times 3. Right? We're just working this expression out exactly. A times D minus B times C. So that's going to give you what? 4 minus 6, which is negative 2. So what does that tell you? It's something other than 0. So that means the matrix A is invertible. So we can say, therefore, let's just, rather than saying A is invertible, let's just say A inverse exists. That's easier to write down. It's much briefer and it means the same thing. Okay, well, what is A inverse? That's a separate question, right? But now at least if we know it exists, then we know it's worth asking that question. What is the inverse of A? Well, now we'll use this formula. So A inverse is going to be 1 over AD minus BC. Well, that's what we just worked out here, right? That's exactly what the determinant is. So we can let's just put a negative 2 here. And then everything else we can follow the formula for. So you swap the entry on the main diagonal. They swap positions, and the other two entries get negative signs introduced, or their signs are flipped. If they're already negative, then make them positive. If they're positive, make them negative, and so on. So that is the formula for our inverse. Let's actually multiply the scalar in. This is the same as negative 1/2 times 4, negative 2, negative 3, 1. So let's multiply the scalar, and just so we actually have the inverse written as a 2 by 2 matrix. So we can write this as -2, +1, 3/2, and then -1/2. And that's how we can express our inverse as a 2 by 2 matrix. There's nothing wrong with leaving it in this form too, because sometimes you might want to leave it that way with the fraction multiplied on the outside as a scalar. You could, in some sense, if you look at this form, there's still an operation left to do, but on the other hand, at least there's no fractions inside here, right? Here we've got everything completely worked out, but now we have two fractions to worry about, one here and one here. So it's quite typical to just write your answer like this as well. But I chose the second form here in this case. But you could use either or, would be totally satisfactory. Okay, so that's an example of finding the inverse of a 2 by 2 matrix, but what about larger matrices? Well, it turns out that you can write down formulas such as this one for larger matrices as well, but the formulas get very complicated very fast, and even at a 3 by 3 case, it's much more complicated to write down the formula, and then beyond 3 by 3, it would just be completely untenable. So what we do instead is we describe a process that you can follow to find the inverse and also determine whether it exists. And this theorem is referred to as the inversion algorithm. And the theorem itself is really just a statement of fact more than an algorithm. But there's an algorithm that's implied by the statement of this theorem, and that's why. And we'll look at that algorithm. We'll look at that algorithm in a moment. But for now, let's read this statement. So it says that, and I've tried to write this as briefly as possible, but there's some assumptions that you'd have to lay out in order for this to make sense. First of all, you'd have to start with a square matrix A, right? So let's assume that A is some square matrix, and you want to know whether it's invertible or not. And if it is invertible, then you want to know what its inverse is. Well, here's the statement that's at the center of everything we're going to do. If you have a sequence of elementary row operations that will turn that matrix A into the identity, and if that's the case, by the way, that tells you something. That tells you that the reduced row echelon form of the matrix A is the identity. So if you can find that, if you can find a sequence of elementary row operations that turns the matrix A into the identity, and then you go back and take that same sequence of elementary row operations, but instead of applying them to A, you actually apply them directly to the identity itself, then what you're going to end up with is exactly A inverse, and that's where the following process comes from. This is called the inversion algorithm. So there's an implied algorithm there. Try to reduce your matrix to the identity. If you're successful, then go back and say, okay, what row operations did I do? Then go to the identity matrix and then carefully apply that same sequence of row operations. That's essentially what's automatically implied here. But there's actually a more efficient way to do it. What we do in general, in practice, is we just do the operations to both A and the identity at the same time. And here's what I mean. So here's an example. We've got a 3 by 3 matrix, and we want to know if it's inverse, if it's invertible, and if it is invertible, we want to know what its inverse is. So what we do, here I'll just fill this in because this is missing. We're going to form the following matrix. I'm going to summarize this formally after, but for now I just want to show you this by example because then it's easier to understand the formal part if you've actually seen it in practice. So notice I'm just writing down the matrix K here. But I'm not going to close it off like that. Instead, I'm just going to draw a vertical line, almost like I'm drawing an augmented matrix of a linear system. But I don't have a constant column here, but I'm just going to put a copy of the identity. Okay, so I've got a copy of the identity matrix, and here's the idea. Okay, I'm going to work on this part, which is where K is, the matrix whose inverse I'm trying to find. I'm going to try to carry this to the identity. And in doing so, I'm going to do the same operations on the right-hand half as well. And in doing so, this will be carried, well, to K inverse, right? Because that's K is the name of the matrix we're actually trying to invert here. So I'm going to focus on this, do some more operations to turn this into the identity, and in doing so, this is going to get turned into the inverse of the matrix K. So, well, how do I turn this into the identity. Let's do the Gauss-Jordan elimination method. So I'll start by clearing out the first column. So I'll take row 2 and replace it with row 2 minus 2 row 1. And then I'll replace row 3 with row 3 minus row 1. Okay, so what's that going to look like? First row is not changing, right? So let's start with that. I'll write it a bit bigger to give myself lots of space. Okay, so take the first row and subtract it from the second row twice. So that's going to give us 0, 1, -3. And then don't forget to do the operations over here as well. We'll have -2, 1, and 0. Right? That's the most common error when you're applying this process is people just leave this as the identity and then they do it for some of the steps but then forget for others, and then at the end you might not notice that you've done that, but then in the end if you miss an operation then what's on the right half of this will not be the inverse, but so make sure you catch it on every operation. Okay, so then now we're going to just subtract row 1 from row 3, so that's going to give you 0, -2, 5, and -1, 0, and 1. Okay, so next what we're going to do is we're going to clear out these two entries. So what we're going to do is take row 1 and replace it with row 1 minus 2 row 2, and then we'll replace row 3 with row 3 plus 2 row 2. Okay, so what's that going to give us? Let me copy and paste this. That'll bring us down here. So what's changing? Row 1 is changing and row 3 is changing. Okay, so what's row 1 going to change into? If we subtract row 2 twice, we'll have 1, 0, 9. And then here, if we subtract -2 twice, we'll have +5, then -2, and then 0. Okay, and then for row 3, we're adding row 2 twice. So we're going to have 0, 0, oops, no, not 1, -1. And then we'll have -5, +2, and then 1. Okay, so now what we're going to need to do is this needs to be turned into a +1. So let's take, that's all we're going to do for this step. So take row 3 and replace it with -1 times row 3. And that will bring us to here. So these will just change the sign of everything in the third row. So wrong color here. Okay, and then now, what do we need to do? We need to turn these two entries into 0. And then once we're done that, then whatever's over here, that'll be the inverse of k. So let's take row 1 and replace it with row 1 minus 9 row 3. Oops, and row 2 we'll replace with row 2 plus 3 row 3. Okay, and that'll bring us where? That will be, so what's changing? All of this is going to change. Okay, so if let's start with the first row. We're subtracting row 3 from row 1 9 times, so that's going to give us a 0 here. This will be 5 minus 9 times 5, so that's 5 minus 45, so that's going to be -40. Then we got -2 minus 9 times -2, that's going to give you -2 plus 18. And then lastly, we'll have 0 minus 9 times -1, so that's going to be 0 plus 9. Okay, then for the second row, the numbers are a bit smaller. We add row 3 to row 2 3 times. That's going to give us a 0 here, -2 plus 15. Then we'll have 1 minus 6, which is -5. And then 0 minus 3 for our last entry. So that tells us now that, hey, whatever, this is the identity now. So that's what tells you that, hey, if you can get the identity, that means it's possible to find an inverse for this matrix K. But guess what? You've already found it by doing the work on this side as well. So now we can say, okay, therefore, this is the fun part, K inverse is equal to -40, 16, 9, 13, -5, -3, and then 5, -2, -1. So that is your inverse. So in doing this procedure, if you're able, remember, so just to recap, if you start with the actual matrix that you're trying to invert along with a copy of the identity. So you try to turn this into the identity, which we were successful in doing. That's how we got here. But in doing so, all along, we do those same operations over here as well, right? And then in the end, what comes out over here is your inverse.